Hello folks, we'll continue with section 6. Okay, section 6 is on lattice, energy and Born-Haber cycles. There are quite a number of learning objectives, so you might want to take note of them over here. Right, so I think C3 need to understand the term lattice energy. So it must be negative. Why is that the case? Because if you look at the definition, lattice energy is the heat evolved when 1 mole of solid ionic solids is formed from its constituent gaseous ions. Yep, so by definition, gaseous ions are very energetic. So when they combine together to form the solid phase, they form ionic bonding. Yep, so bond formation leads to a release of large amounts of energy. Right? The second learning objective you have over here is you need to explain the effect of ionic charge and radius on the numerical magnitude of the lattice energy. You briefly learnt about lattice energy in topic 1 under atomic structure. So over here, we will make use of a relationship where lattice energy is directly proportional to the product of the charges and inversely proportional to the sum of the interionic distance to help us determine the numerical magnitudes. Right, then finally, apply Hess's law to construct simple energy cycle in the form of a Born energy cycle to carry out calculations. Then there are 2 new terms you need to come to terms with. Electron affinity. Okay, so IE you have learned about that, so just 1 new term. Okay, so we'll just go through the rest of the notes in some details. Lattice energy is always negative. I explained that to you earlier on, because gaseous ions are very energetic and the formation of ionic compounds leads to release of energy. Okay, so in general, the more exothermic the lattice energy, the stronger the ionic bond. So that's what we need to understand. So moving to 6.2, the factors affecting lattice energy. So there are 2 factors, the charge and the size. So this is a relationship you need to be familiar with. So lattice energy is directly proportional to the products of the charges, inversely proportional to the sum of the interionic distance, or the sum of the ionic radii. Okay, so in our case here, if you look at sodium chloride versus magnesium chloride, you'll notice that the product of the charges for sodium chloride is 1, that of magnesium chloride is 2. Okay, then both of them are chlorides, so the n ionic radii is the same. Okay, yeah, but because the n ionic radii is the same, we now focus only on the size of the cation. So is it possible to then reduce the relationship? Not possible, because the denominator is a summation. Yeah, so but based on this alone, you know that the sum of the ionic radii for magnesium chloride is less than that of sodium chloride. Yeah, so because it's an inverse relationship, I would expect for the sum of the ionic radii, lattice energy to be more exo, and the product of the charges for magnesium chloride is also bigger. Yeah, so based on this alone, both the sum of the ionic radii as well as the product of the charges point towards the fact that I expect magnesium chloride to have the more negative lattice energy. Okay, which is shown to be the case. So these are the one you can either Google them or you can find them from other sources. Okay, yep. So hope you know what to focus on. Okay, so I think I'll just move on. Nothing much to say about this. Okay, Born-Haber cycle. So it can usually be determined through Born-Haber cycle. For the purpose of this, usually the Born-Haber cycle is in the form of an energy level diagram, where you need to have the 0 reference line over here. So this is the elemental line. Okay, so nothing much to say. Later on, I will perhaps showcase to you how to draw a simple Born-Haber cycle. Okay, maybe I can illustrate it over here in the small space here for sodium chloride. Okay, so first of all, I will have the vertical axis. Yep, so this will be the energy term. Okay, so energy. Okay, in terms of kilojoules per mole. Okay, so this is the vertical axis. Maybe I'll use a ruler. That might be a bit easier. Okay, so where's the ruler? Okay, so yep, vertical down. Oops. Just give me a while. I think there's some issues related. Okay, just give me a while. Okay, yep. So down. Oops. Okay, vertical down. Okay, then I have another line here. Okay, then this is the 0 points. Okay, so for sodium chloride, maybe first of all I will do a simple illustration like this. Okay, I will have the simplest way to do it is to have three areas you need to be you need to be comfortable with. This is one line, two somewhere below, and another one over here. Okay, well, why is that the case? Because I want to define enthalpy change of formation as well as lattice energy. So this is Na solids plus half Cl2. I hope you can see that you need to be very clear of your definition. So if you're not clear of your definition, it might be a bit difficult. Okay, so I need to define this and I need to define this. Okay, so I'm going to use the ink here. I need to define these two terms. Okay, I'm going to use blue. So this is lattice energy. So Na plus gaseous plus Cl minus gaseous. Okay, so this is NaCl. Yeah, defining these two is easiest. Okay, and it's the most common technique, or it's the most common way we start off the drawing of the Born-Haber cycle. Okay, so define the enthalpy change of formation. So that involves 1 mole of sodium atom and half a mole of chlorine, diatomic chlorine. Then define lattice energy. So that is gaseous at sodium cation as well as chloride and ion. Okay. Then after that, the goal is to move. Okay, so called to move from here to here. Okay, so this will be a bit more difficult, or rather, you need to be a little bit meticulous when you try to shift from over here to over here. Yeah, because that actually involves several energetic terms. So if you aren't careful, you might make some mistake. Okay, so again, my suggestion is perhaps to begin with, maybe you can try atomizing sodium and chlorine, because once you change them to atomic gaseous atom or gaseous atom, it's easier to maneuver towards the respective cation. So what I'll do here is I will first move up. Okay, so over here I'll write it as Na gaseous and Cl gaseous. Okay, so I'll just move up here. Okay, so this is defining the enthalpy change of atomization for sodium as well as the enthalpy change of atomization for chlorine. Okay, or it can be viewed as half, or it can be viewed as Born energy times half. Okay, if you remember the definition of enthalpy change atomization, you will know why. Okay, if you couldn't really understand why, you might want to go back and review the relevant section of the notes as well as the lecture videos. Okay, then from here I need to define first IE, so I need to go up. Okay, so first IE, so that's Na plus gaseous plus electrons plus Cl gaseous. Okay, so I need to move up, and then that is the first IE of sodium. In case you don't know where to find the information, it's in your data booklets. So if you just scroll down, this is the first IE. Okay, so the information is over here. 494 kilojoules per mole. Yep. So IE information, please look up the data booklets. Okay, then you define electron affinity downwards. So this is first EA of Cl gas. Okay, so once you define everything, then you can use Heft's law to solve for whatever energetic term they require you to solve. Yeah, so this is the generic way of drawing the Born-Haber cycle for sodium chloride. Right, so I illustrate it here. I think it might be easier as compared to a diagram like figure 4, because figure 4 just already drawn in for you, but now I do a illustration so you can see. Okay, so we have IEs. We already defined what IE is. Energy required to remove 1 mole of electrons from 1 mole of gaseous atom to form 1 mole of uni-positively charged gaseous cations. So IE always positive. Electron affinity is energy required, or rather it's the enthalpy change when 1 mole of electron is added to 1 mole of gaseous atoms to form 1 mole of singly charged gaseous anions. Okay, or negatively charged anions, if you want to put it that way. It's usually negative, depending on the situation. Yeah, so why? Because the electron comes in, and then the nuclear charge actually strengthens the attraction between the nucleus and the electrons. Yeah, but subsequently, right, second electron affinity could be positive. Yeah, because for example, in the case of oxygen, after it becomes O-, you are forcing another electrons into a negatively charged anion, right? Then you need to input some energy to overcome the electrostatic repulsion between the two negatively charged species. So second EA tends to be positive. Yeah, tends to be, not always the case. Okay, right? So moving on. Okay, so we have exercise 6.1 already illustrated for you. This is for sodium oxide, so maybe I'll just point to you some facts. You might want to check them out. Okay, you are already given information such as you need to check what information you are given. You are given atomization enthalpy, first and second electron affinity of oxygen, as well as enthalpy change of formation of sodium oxide. Okay, so once you draw the cycle, the thought process is really, maybe I'll just highlight. Draw this zero line first, okay, including the species. Draw the product first, okay, as well as draw the gaseous ions last. Okay, so once you have all this in, you notice that I already defined this portion as well as this portion. Okay, so once they are defined, then your next job is to move from here all the way to here. Okay, moving from the respective elements, right, to the cations and anions is not that straightforward for beginning students. So you have to be very meticulous and go and count. So for example, you are given the atomization enthalpy of sodium, and then now you notice that 2 sodiums involved, so you need to multiply this by 2. Okay, and then you are breaking the OO covalent bond, okay, and then you have to form the gaseous atom. So because you are only overcoming half moles of O2, so you need to multiply the bond energy by half. Yeah, that is provided the enthalpy change or atomization of oxygen is not given to you. If it's given to you, then you will use that information instead. Okay, then after that, you need to go and look at your IEs for sodium, which is 494, and then because you are expelling out 2 electrons, so you need to multiply this by 2. Yep, and then for electron affinity, okay, another common mistake students tend to make is they forget about the electrons, so make sure that you have your electrons in. Okay, so you gain 1 electron, it's negative, you gain the other electron, is positive. Try to have them separate, don't combine the 2 terms, although combining, strictly speaking, is not incorrect because you are kind of allowed to combine similar energetic term, but usually to the best of your ability, try to do them separately. Okay, try to write them out separately, then it looks neater. Okay, then after you just use Heft's law to sum them up, and then you should get the lattice energy of sodium oxide to be negative 2567 kilojoules per mole. Okay, you can leave it to 3 or 4 SF. Right. Okay, let me see what else. Okay, the 0 point is important here, so make sure that you include that in your answer. Okay, then I will illustrate, I will construct the Born-Haber cycle for the formation of calcium chloride from its elements and calculate its lattice energy. I'm given the atomization enthalpy, formation of calcium chloride, and first EA of chlorine. The other information I need is probably the first and second IE of calcium, so that will be 590 and 1150. So I will take note of this. Okay, I will use the space here to try to illustrate, although might not be the best. Okay, so let me just try to write it out clearly. So this space here, okay, and then let's see. Okay, I put the arrow. Okay, so this is energy. Okay, kilojoules per mole. Okay, then I'll have the 0 points. Okay, then I'll put a 0 here. So I'm defining this enthalpy change of formation first. Okay, then I'll draw another line here. Okay, I'll draw a longer line. And then I'll draw another line here. Okay, so I'll write these two terms. This is CaCl2 solids. So this is defining the enthalpy change of formation. So that's minus 796. Okay, then this is Ca2 plus gaseous as well as 2Cl minus gaseous. Okay, then this, let me draw this line properly. Okay, so this is what I need to find out. So this is the lattice energy. So I'll just color code it Le, lattice energy. Okay, then what I'm going to do now is I'm going to travel from here to here. Okay, so let's see what I'm going to do. So I'll color code with a different color. So first I will perform atomization. Okay, so atomization, I'm going to get Ca gaseous and chlorine. So chlorine, I need to look at the bond energy. So the bond energy of chlorine is given to be over here, 244. Okay, so I'm forming 2 moles of gaseous chlorine atoms, so that would be 244. So 244, and then 178. 178 is enthalpy change of atomization for calcium. Okay, then after that I will need to perform my IEs. So I will need the two first and second IE of calcium. That's 590 and 1150. So I'll just arrow upwards. Sorry that it overlaps a bit. Okay, so that is Ca2 plus gaseous plus 2 electrons plus 2Cl gaseous. Okay, so this value will be 590 and 1150. So I'll put here 590 and 1150. Alright, then after that, first EA of calcium, chlorine, so that's negative 349. So I have 2 moles of chlorine, so negative 349 times 2. Okay, so therefore I'm going to define my I'm going to calculate my lattice energy. So I'm going to use orange. So I'm going to go in this direction, so going downwards, right? So I'm going to go like this, and like this. Okay, if it's against the flow of the arrow, then I'll switch the sign over. So lattice energy is therefore equals to 349 times 2. Okay, then minus 590 minus 1150 minus 244 minus 178 minus 796. Alright, yep, then I'm going to punch my calculator. So therefore lattice energy is equals to negative 2260 kilojoules per mole. Okay, yep, so I hope you get the rough intuition in drawing the Born-Haber cycle. Yeah, so first I will do it in green. Normally I'll look out for 2 important pieces of information: lattice energy as well as enthalpy change of formation. I'll start from the reference point, there's a 0 point where the elements are. So in this case it's calcium and chlorine. And then I will define enthalpy change of formation as well as lattice energy. And then after I define it, I will incorporate the relevant ions in. That is the gaseous calcium 2 plus and chloride. Then after that I will make my way from the elemental calcium and chlorine all the way to Ca2 plus gaseous and Cl minus gaseous. And then after that I'll input the relevant values into my Born-Haber cycle. So this is a good practice you can follow by inputting the relevant values, and then after that you solve it by Hess law. Okay, hope that is alright. Then section 6.4, we have experimental versus theoretical lattice energy. Okay, so the experimental lattice energy is something you obtain through the use of the Born-Haber cycle, and these are experimental values, okay, of the relevant energetic terms lah, right? Theoretical lattice energy, it's something that we determine or calculate based on a model that is assuming that the compound is completely ionic. Completely ionic here also means that they are point charges, and there is no covalent character present. As you have learned in chemical bonding, for cations, we are looking at this term known as polarizing powers. Okay, cations, we are looking at polarizing power. Polarizing power is defined as the ability for a cation to distort an electron cloud. So the greater the polarizing power, the greater its ability to distort electron clouds. Okay, anions, we are looking at polarizability. Okay, so polarizability is the tendency for the electron cloud to be distorted by a cation. So the larger your electron cloud is, the more polarizable the electron cloud is, then the more easily is being distorted. Okay, so that is important, you need to be aware of. Yeah, so in theoretical calculation, we assume that the charges are point charges, so they are not distorted at all. Yeah, but in real situation, you know that all the cations have some sort of polarizing power, whether is it strong or weak, it's dependent on where it is placed in the periodic table. And the anions have large electron cloud size, so they tend to display relatively large polarizability unless they are very small and compact. Yeah, so there will be some form of covalent character in an ionic compound, and therefore the greater the covalent character, the greater the deviation of the experimental lattice energy from the theoretical lattice energy. So these are some examples we have here. So for example, silver fluoride and silver iodide. You notice the great deviation between silver iodide from silver fluoride. Yeah, because fluoride is very compact, so it is very low in polarizability, but iodide, large electron cloud, it can be easily polarized. So based on this, based on these two data, you can conclude that silver iodide has a greater degree of covalent character as compared to silver bromide. Okay, so same case goes for the comparison between magnesium chloride and cesium chloride. If you look at cesium chloride, it is the experimental lattice energy almost matches that of the theoretical lattice energy, for a very simple reason, because cesium plus has very low polarizing power. Yeah, so very low polarizing power means that the chloride electron cloud cannot be easily polarized. Yeah, so I would expect the experimental lattice energy to match quite closely with that of the theoretical one. But for magnesium chloride, because Mg2 plus has relatively large polarizing power, so it's able to distort the anionic electron cloud to a relatively large extent, giving it more significant covalent character as compared to cesium chloride. So from here you notice that there is a deviation between the experimental lattice energy from that of the theoretical lattice energy. Okay, so this is being explained in these two bullet points. Right. Okay, so almost done with the chapter. We are going to move on to section 7 next, on standard enthalpy changes of hydration and solutions. Yep, so this will follow two learning objectives. You need to explain and use the term enthalpy change of hydration, and that is defined over here. The heat evolved, so it's an exothermic reaction where 1 mole of free gaseous ions is completely hydrated, or you can put it as dissolved in infinite volume of water, so at standard conditions, 298 Kelvin, 1 bar. Okay, why is it that you are expecting it to be exothermic? Well, I mean, remember earlier on we mentioned that gaseous ions do not have any objects surrounding it, right? So when you put it in the water, what's going to happen is that the delta minus of water molecules on oxygen will form favorable ion-dipole interaction with the sodium cation in the case of sodium plus, and then for chloride it will be the delta plus of the hydrogen in water that will form favorable ion-dipole interaction. So bond formation is exothermic. So for standard enthalpy change of hydration, we're expecting The we're expecting it to be an exothermic reaction. Yeah. Then the next learning objective, you need to construct a simple energy cycle, etc. So it's the same thing. Application is on Hess law. Okay. So you're given two examples here. Sodium plus and bromide, both cases, and hydration enthalpy negative. Okay. So due to the ion-dipole interaction. Do take note that when you are drawing the ion-dipole interaction, it is important for you to highlight at least one dipole here. Yeah, and then if possible, include the lone pair in as well. Okay, because the ion-dipole interaction originated from the lone pairs of electrons of oxygen facing the sodium plus cations. Okay, and then, so these are the important thing. You need the labels. You need to indicate where are you labeling. You need to indicate the dash lines. You need to indicate the lone pairs. You need to indicate the delta minus, delta plus, and then minimally you might need a sodium cation and you might need a water. Okay, so do take note of what you need, at least for assessment. But of course we are learning now. Go ahead and make all the mistakes you want, but during actual assessment, just make sure that you remember some of these little details. The magnitudes of the enthalpy change of hydration depends on the charge density. So in chem bonding we talked about it before. Okay, what exactly is charge density? So it's directly proportional to the magnitude of the charge and inversely proportional to the ionic radius. Okay, so this is probably an important relationship you need to be aware of. Sometimes students when they are learning it quickly, they might have missed this important relationship. Okay. Then of course, the higher the charge density, you are expecting the stronger the ion-dipole interaction, because there is a stronger tendency to form stronger electrostatic forces of attraction. Okay. Yep. So we know that sodium plus 0.095 nanometers, Mg2 plus 0.065 nanometers, right? And sodium plus 1 charge, Mg2 plus 2. So I expect the charge density of Mg2 plus to be greater than sodium plus, and this is reflected by the enthalpy change of hydration. Okay. Then moving on to 7.2, we have the standard enthalpy change of solution. Yep, so by definition, enthalpy change when 1 mole of the solutes is completely dissolved in infinite volume of the solvents here. Okay, so the solvent here need not be water, but in most cases, based on the examples we often use and based on the chemistry we are dealing with, at least as a JC students, usually it's water. Okay, but it can be other solvents. That's why the definition here is infinite volume of solvent, but for hydration, we highlight infinite volume of water. Okay, yep. And then you take on some values here. It can be positive, it can be negative. It really depends on the nature, okay, of the dissolution. Okay, which terms outweighs which term? Is it bond breaking requires more energy than bond forming? The bond breaking here will be referring to ionic. The bond breaking here will be referring to ionic bonding. The bond formation here will be referring to the formation of ion-dipole interaction. Okay, yep, then the solute is usually an ionic compound, where solvent is usually water, usually. Yeah, it can be other things. You can have enthalpy change of solution for an organic molecule as well. It need not be ionic compound, just to make sure. Yeah, so this is usually the case. The reason why is it usually the case, at least for H2 chem, is because this is what we are usually dealing with, but it's not always the case. Okay, yep, then okay, this is a proxy. It's not a gospel truth. Take note of this. If it's highly positive, salt is likely to be insoluble. Negative, likely to be soluble. There are other aspects to look into. So not always true. So take it with a pinch of salt. Yeah, literally. Okay. Yeah. So there are salts with positive enthalpy change of solution are soluble. For example, potassium. Usually all the nitrates are very soluble. Yeah, and the reason is because there is another factor that's coming into the play, and that is entropy change that will be introduced in section 8. Okay, 7.3 here, relationship between lattice energy, enthalpy change of hydration, and enthalpy change of solution. Okay, this is quite important, but again, my advice is do not memorize it without understanding what's going on. Okay, so yeah, so I just follow through, and then you see whether you can understand. Okay, now they went, okay, so quite a lot of things are mentioned here, so maybe I can just highlight this in a cycle so that when you read through the notes it's not so confusing. Okay, so we understand from the definition, so maybe I'll just look at sodium chloride. Okay, we'll understand from the definition of enthalpy change of solution. I'll just start with sodium chloride. Okay, so that is the solid becoming the aqueous ions, right? So I will start by drawing it over here, the cycles. Okay, so I have sodium chloride, solids. Okay, I define enthalpy change of solution. Okay, then I'm going to end up with Na plus, aqueous, and Cl minus, aqueous. If you remember, we can also define lattice energy for ionic solids. So lattice energy here will be defining as Na plus gaseous plus Cl minus gaseous. Okay, so that's lattice energy. Yeah, right? And then over here, we can link them up. So this is the enthalpy change of solution for Na plus gaseous. This is the enthalpy change of solution, sorry, enthalpy change of hydration for chloride. So this is hydration for chloride, gaseous. This is enthalpy change of hydration for sodium plus gaseous. Okay, then with that, if we want to find out what is the enthalpy change of solution, we can then just draw this cycle. Okay, so enthalpy change of solution would then be equals to negative lattice energy plus the enthalpy change of hydration of the sodium plus, as well as enthalpy change of hydration of chloride. Okay, so we end up with this particular relationship. Okay, yep, then you can see that this is what you end up with. Okay, it can be so-called proven using a cycle. Yeah, so again, this equation, no need to memorize. Derive it. Yeah, assessment purposes, just derive it. You can come up with a energy level diagram as well if you wish to. Yeah, I mean, it's perfectly fine. The only difficult part is if you are required to calculate the enthalpy change of solution, you don't know if it's positive or negative. So sometimes if you draw up and then when you do the calculation it turns out to be negative, then you have to erase your diagram and then draw it down. Yeah, so it might be a bit cumbersome. Okay, so where possible, try to solve it using the cycle, unless you are forced to use energy level diagram. Okay, yeah, then there's a work example here, which I think there's an illustration, but I'm just going to combine some diagrams here, so I hope you can see the thing as a whole, because I use sodium chloride. Okay, so I'm just going to draw for you the Born-Haber cycle, incorporating the enthalpy change of solution and hydration. Okay, so I'm going to use a generic example, sodium chloride. So I have energy here. I'm going to draw in green, kilojoules per mole. Okay, so this is very good for revision, because when you try to revise, then you notice that if you can verbalize some of the thought process, then you are able to complete your revision double quick time. Okay, then over here I have enthalpy change of formation of sodium chloride, so I'm not going to spell out so many things. Sodium chloride. So do you remember that I mentioned that it'll be good for you to start off with the lattice energy? So this is the lattice energy. Okay, so this is sodium plus gaseous plus Cl minus gaseous. Okay, then I'm going to have the enthalpy change of atomization. So I'm going to get sodium gaseous plus Cl gaseous, and then I'm going to get the enthalpy change. Okay, I'm going to draw it higher so that it's not so ugly. Lattice energy, sorry, not lattice energy, IE, first IE of sodium gaseous. Okay, then end up with Na plus gaseous plus electrons plus Cl minus, Cl gaseous. Okay, then I'm going to get first EA of Cl gaseous. Okay, yep. Then I'm going to use another color, orange. So I'm going to use this part to complete the enthalpy change of hydration. Okay, so you know that if I'm going to have another line here, Na plus aqueous plus Cl minus aqueous, then this will be defining the enthalpy change of solution, and this will be defining the enthalpy change of hydration of Na plus gaseous and Cl minus gaseous. Okay, so this sort of, if you are able to do this at free will when you are revising, right, actually you already cover about 1/3 of the topics. Yeah, so I do encourage you to go through this on your own without referring to your notes, and at the same time verbalize the definition, because you need to know the definition in order to complete the hair cycle. Alright, so pretty much we're done with this. Finally, what examples, answers given, I'm going to briefly go through. Anyway, you have heard me just now talking about it over here using this cycle. So it shouldn't be a huge issue, so I just verbalize what I've said again. So you're required to use an energy cycle, calculate the enthalpy change of hydration of the chloride given the following data. So again, sodium chloride. I'm sure it needs no introduction that you need to put all this here, right? So exactly the same as what I did earlier on. Okay, then what else do you need? Okay, so plus 5, input the values, then negative 390 for the enthalpy change of hydration for sodium, plus, okay, as well as negative 776 for the lattice energy. Okay, so what you do here is you just, if you want to do it like this, you can. Okay, so that will be, I prefer to do it like that. So what I'm going to get here is 5 is equals to 776 minus 3990 plus enthalpy change of hydration of chloride. Yeah, so I can do it like that as well. It doesn't really matter how you go about doing that, as long as you get the correct answer. Okay, can? Yeah, so we're getting a value of negative 381 kilojoules per mole. So part B, enthalpy change of hydration of iodide was found to be negative 296. Comment on the difference. So again, whenever they ask this question, yep, you know that you need to incorporate this relationship in your answers. Okay, so you need to highlight that I minus have same charge but larger ionic radius. So the ion-dipole interaction is likely to be weaker between I minus and water molecules. Okay, because the charge density of I minus is smaller than that of chloride. Yeah, so because of that, the hydration enthalpy is found to be less exothermic. Okay, you take note of the term I use. I do not say that this value is less than this. I say that it is less exothermic. Okay, less exothermic than minus 381. Or you can say numerically smaller. Yeah, so there are two ways to present it. Don't say smaller or bigger, because you don't know, are you looking at it from a number line perspective or from an absolute magnitude perspective? So highlighting that it's more exo or less endo, or numerically larger or smaller, it helps more. Alright, so with that, we have come to the end of section 7. So next, we are going to look at section 8 in the next video.